Thank you for the introduction. I welcome you to my presentation about an algorithm of generalizing road networks. This is a joint work by Thomas van Dijk, Jan-Henrik Haunert, and me. I'd like to start with a cartoon you probably recall from the Fast Forward session. A car driver in Berlin is asking for directions to Paris, and he gets the response, of course, what's your exact destination address? Why should someone in Berlin, being asked about the directions to Paris, bother about the exact destination address? When most of the paths from Berlin to any address in Paris are basically the same. They only differ close to Paris. Okay, we thought about this problem and we came up with the idea of contracting vertices if the distinction is not meaningful. That means we want to contract vertices who share a lot of shortest path. If we take a look in related literature, we find a lot about road selection, and we also observe that road selection in general is NP hard. Furthermore, we found a lot about variable scale maps, where the level of detail and the scale are adapted to the region of interest. As we want to make a user location dependent map, this is useful for us. Another keyword I would like to drop is destination maps. Here in this specific example, roads are selected based on shortest paths to a destination. Apart from that difference, this is closely related to what we do, but the problem here is that we do not have any guarantee of optimality. Okay, so we start with a road network where we have some user location within it, and we take a look at shortest paths from this user location. But we're not interested in those shortest paths from S to any other vertex, but to those shortest paths to any point in G. This structure we gave the name T for tree, and we will use it throughout all of the presentation. Okay, so we are given a tree rooted at some vertex S, which may look like this over here. In this specific example, all edges have the same length. On this tree, we define directed similarity from a vertex U to another vertex V, which gives us information about how much of the path from the root to the vertex U matches the path from the root to the vertex V. If we take a look at our example here, this is from the root, 1, 2, here comes the fork, 3, 4, 5. So we have 2/5 of the path from the root to U, which are shared. If we take a look the other way around, considering the directed similarity from V to U, we notice that the shared path is the same, of course, but the path to V is shorter. Hence, we have a directed similarity of a half. You probably might have noticed that the lowest common ancestor X plays an important role in that definition. But we are interested in a symmetric criterion, therefore we introduce alpha compatibility, and U and V are called alpha compatible if both of their directed similarities are at least alpha. So for our example here, alpha has to be at most 2/5 in order for U and V to be compatible. If this value alpha is clear from the context, we just say that U and V are compatible. Okay, with this criterion we can define another graph, the compatibility graph. It has the same vertex set as the original input tree, and we add one edge per pair of vertices which are compatible. Furthermore, we define a subset of vertices to be allowed to be contracted if and only if this subset of vertices is connected in our tree and it's a clique in G+. Clique means that any two vertices of this set share an edge in G+. I'll show you some examples. We start with this set of 3 here. This is a clique of 3, but they are not connected in T. Therefore, we do not want to merge them, to contract them. Because if we would contract them, we would end up with a contracted cell where we have to leave the cell in order to get from one end to the other. And that's not what we have in mind. Another bad example is this. This is connected in T, but we do not have a clique in G+. In particular, this edge is missing. As compatibility is the criterion for which we want to contract, we do not want to contract here either. And finally, some good example. Here everything's fine. The set of 4 vertices is connected in T and forms a clique in G+. Important, G+ is depending on the alpha value, and for this specific example we chose alpha to be 2/3. Okay, so what have we got? We have some tree which is rooted at some vertex S. We have non-negative weights on the edges, and we have a compatibility threshold alpha. The problem that arises now is to find a partition of V into as few cells as possible. That means we want to contract as much as we can, as much as we are allowed to. Before I can show you our algorithm, I need two lemmata. The first one states that 2 vertices U and V are compatible if and only if both of them are compatible to the lowest common ancestor. This follows basically directly from the definition. The other lemma we need is about some vertex X and its descendants. And if we know of some descendant B of X, over here, you can see it in the example, that it is compatible to X, then we know for any descendant of X which is as most from as far from X as B is, that it's compatible as well. This means in this specific example, if B is compatible to X, then any of the red vertices are also compatible to X. And combining this with the first lemma, we know that each pair of vertices of this subset is also compatible. That means those vertices form a clique in G+. Okay, now we can start with the algorithm. This is the beginning the situation at the beginning. The blue cells symbolize a cell which we want to contract. So this is a valid solution, though not a very sophisticated one. Our algorithm traverses the tree in post order, which means that we start at the leaves and proceed towards the root. For example, we start here with this leaf, and as our algorithm handles the children of a vertex, we can continue to the next vertex. And here we take a look at the children of this vertex. This here, for example, we see it's connected, and we see in the compatibility graph that they are compatible, so we're allowed to merge them, and we do so. If we now want to add this vertex to this cell, we notice that we have to check compatibility actually for those 2 vertices. But as we know from the first lemma, it's sufficient to take a look at the lowest common ancestor. And here we see it's compatible and connected, so we're allowed to merge it. So this vertex is done, and we can proceed to the next vertex. Okay. The first child is easy again, the right one, compatible and connected, so we merge it. And when we consider this situation, we notice that we have actually to do 3 comparisons. But as we know from the second lemma, it's sufficient to take a look at a deep vertex. So actually we only have to do 1 single comparison. And here we note it's compatible, and it's connected, hence we merge it. You probably might have noticed that in any step of our algorithm up to now, we have some invariance holding. Firstly, the vertices of a cell are always connected in T. The reason for this is simple. We only merge vertices with the cells of their children, and consequently they are connected. The second invariant is that this cell always forms a clique in G+. As this follows from the second lemma. Okay, now we can proceed to the next vertex. The first one, again, is easy, compatible, and connected, and we merge it. And when we want to do this comparison, we have to look again at the deep vertex of this cell, or at one deep vertex of this cell. And here we note that this deep vertex is not compatible to the lowest common ancestor of those vertices. Hence, we are not allowed to merge them or to contract them. Okay, now we're done for the right branch. The algorithm continues for the remaining leaves, and in post order, as I told you. And finally, we get this result. Okay, so what have we done? We started with a set of singletons, and then our algorithm traversed the tree in post order. And for every vertex x in T, we did exactly one comparison. We took a look at, for every child of every vertex x, we did exactly one comparison. We did the comparison, which is written down here. We took a look at the deep vertex of the cell of the child, and if it was compatible to our vertex in question x, then we merge them. Okay. As we have only one comparison per child, we have linear runtime here. So we've got an output, and now I want to show you that our output is optimal. So C is what we've just computed, and as we know from the invariance, this set C is a set of cliques. It's a clique cover of G+. And now I want to show you to you that this clique cover is a minimum clique cover. Therefore, we consider some set I, which contains one deep vertex per cell of C. And I claim that this set I, which is depicted here by red vertices, is an independent set in G+. If it weren't, we could find a pair of vertices U and V in I, which share an edge in G+, which means that they were compatible. Consequently, we can also find the lowest common ancestor of those two vertices, which we denote as x. And from the first lemma, we know if U and V are compatible, then both of them are compatible to x as well. Okay, but as U and V both are deep vertices, we would have merged them when the algorithm arrives at x. So this is a contradiction to the assumption that both U and V are elements of I. So I is an independent set, has to be. Furthermore, we note that I is of the same size as C. That follows directly from the definition of I. So we found an independent set which has the same size as our clique cover. Consequently, our clique cover is a minimum clique cover. Okay, now we got our result. Now we want to visualize it. We want to contract the vertices to one vertex. There we choose the root vertex, here in blue. And we observe that the relation between those root vertices is a tree structure induced by our input tree T. But how can we visualize this tree? We came up with three different ideas. The first one is, we call it the detailed drawing, where we draw the shortest path from every from every root to its from every root of a cell to its parent. Okay. The advantages of this drawing are obvious. We don't have any additional crossings as we use the original tree. And thus we have the same level of detail as the input, which might be considered positive or negative depending on the application. What is a disadvantage are those internal branches, with which we mean the situation here, as we've put a lot of effort in our algorithm to eliminate shared paths. And here we have them again in our output. Therefore, we came up with a second idea, we call it the direct drawing, where we draw a line from a vertex C to its parent. Okay. This is simple and highly generalized, and it shows what we've actually done. This is the output of our algorithm. But we have additional crossings, which you can't see in this example, but I'll come to that later. And another disadvantage is that this drawing is not order preserving. If you take a look at the real output, the detailed one, the order of the vertices is 1, 2, 3, 4, 5, 6 in clockwise. Yeah. And if we take a look at the first two vertices here, those are the third and the fifth vertex in the direct drawing. Okay. Therefore, we came up with a third idea, which we call the simplified drawing, where we take the detailed drawing and apply a topologically safe simplification algorithm to it. Because of the choice of the algorithm, this drawing has no additional crossings, and it's order preserving. That it has fewer internal branches is positive as well, but we cannot guarantee to get rid of them. Therefore, I marked it neither positive nor negative. What's negative for sure is that it's a heuristic, because up to now we were working optimally. Okay. Apart from that, I would like to introduce cross connections. If we draw just a tree, we lose a lot of information. If you take a look at those contracted cells here and here, they touch in 3 points in the original tree. But we have no information about that in our output. And we can solve this problem by drawing a cross connection for neighboring cells. Okay, but enough of this theory, and we take a look at the results. Firstly, we compare the direct drawings for various values of alpha, and we start for alpha equals 50%. If we increase alpha from 50 to 70%, you notice that the level of detail increases close to the root, and also that the branches of the output tree grow longer. The same effect is observable when we increase alpha from 70 to 90%. Okay. Now I want to show you the other drawings. So on the right hand side we keep the direct drawing for alpha equals 70%. You already know that. And on the left hand side I will show you the detailed drawing now. Okay, and here you can see the advantages and disadvantages I've pointed out. It's the same level of detail as our input map, but we can hardly detect what our algorithm has detected as a vertex, as the cell root. Okay. Before I show you the simplified drawing on the right-hand side, I would like to focus your attention to this particular area. Here we have a crossing, where in the detailed drawing, and consequently in reality, there is no crossing. And we can solve this problem with a simplified drawing. Besides that, the simplified drawing looks pretty much like the direct drawing. Okay. The last example with this dataset is one with cross connections, and they appear now. Okay. And I think on the left hand side we have something which pretty much looks like a regular map we are all used to. And what else can we do with the map like that? Therefore, I show you another example with the city of Dallas, where we applied our algorithm for alpha equals 50%, and afterwards applied variable scale map projection. This has the advantage that we can enlarge the area of interest, which is close to our user location, and the region farther outside get distorted, but that's okay because that's not where our focus was. And our algorithm made this possible because we filtered the set of roads there. Okay, so what have we done? First, I presented you the problem of contracting compatible destinations. I showed an optimal linear time algorithm to you to solve this problem, and I have presented some ideas to draw that. That's it from my side. I'd be glad to answer any open questions. Thank you for your attention.